The short answer is you already know what the disk method is. You've been doing it. What did we do right here? We found the area of a disk and integrated it. We're just formalizing this in mathematics. So I'm going to introduce the disk method here. You don't even need this because you've already been doing it. And there's a lot of requirements, so I want to talk a little bit about each of these as we're introducing them, okay? Let f be continuous and non-negative. So let's start with that. What happened? Why is that necessary? Continuous and non-negative. Well, because if this function, this f here, is not continuous, well, then we can just break it up into different pieces, or if it's not continuous anywhere, then we're not going to really have volume as we think of volume. So in order to have just a single integral, we'll want it to be continuous. And non-negative is important because we get weird things if we start rotating under an axis. And again, that's another situation where we'd split things up and we could handle it that way. Okay, so define R as the region bounded above by the graph of f and below by the x-axis. This is basically what we've been doing. On the left, by x equals a, and the right, by x equals b. Again, this is exactly what we did in the last problem, right? Bounded above by this, bounded below by the x-axis, bounded to the left by this, bounded to the right by this. We're just formalizing this. Okay, we've already done this. Just making it very formal here. The volume of the surface of revolution is given by the following. V equals pi times the integral from a to b of f of x squared dx. All right, so it's just formalizing what we've done. I wouldn't even recommend memorizing this formula. Just doing it like this every single time is probably what I would recommend. It won't even take that much longer, just a little bit. But again, this is exactly what we did, right? This is just pi times the radius squared. Because our cross sections, if we look at things this way, our cross sections are going to be volumes or circles. So again, this is exactly what the disk method gives you. Just if you want to jump right there. And special note, if rotated about the y-axis, the x-axis, and we have a very, very similar formula if we're rotating it around the y-axis. C to D, again, it's the same region bounded, but C and D are going to be a little different. And now it's just going to be some function. We'll use f, I guess. F of y dy really should have a different setup if it's about the y-axis, but the idea really is exactly the same. So if rotated or revolved about the y-axis, it's just the same. You just set it up in terms of y instead. So we're going to do some problems, see this in action. But again, nothing is new here. Just a formalized method for those of you who want it. Example 5. Find the volume of the surface, solid, not surface of revolution, solid of revolution, where in part A, R is the region bounded by the square root of x the x-axis. The lines x equals 4 and x equals 1. And rotate about the x-axis. We're going to draw a picture. All right. We're going to draw our picture. See what happens. We're looking at square root of x, which looks like this. And we're saying we're starting at x equals 1, going to x equals 4, and we're rotating it about the x-axis. So one of the ways that we can denote that is a little rotation like this. So the picture, right, is going to be this blue guy. And again, it's mirror down here, being rotated about that axis. Again, we have the same cross-sectional circle or disk we always have. And the height is just a function value, just like always. So that's the picture. That's what's going on. We can use the disk method here because we have a continuous function. It's non-negative. What else do we need? It's bounded exactly as we said it should be bounded. So if you didn't want to say, well, look at the area of this cross section, it's pi times the radius squared, where the radius is the y value, which I would recommend you do. But if we want to use the disk method directly, we just say the volume is the integral from 1 to 4 of pi times the function squared with respect to x. And that's pretty quick. Square root of x squared is x with a domain restriction, but we're going from 1 to 4 anyway. So in this case, if on 1 to 4, the square root of x squared is exactly the same as x. Antiderivative of x is 1/2 x squared, evaluated from 1 to 4. We can factor the pi over 2 out in front, and then just look at 4 squared minus 1 squared is 15. We should get 15 pi over 2 is our answer. Again, we can always double check with a lot of different ways. One of them is to do pi times the integral from 1 to 4 of the square root of x squared dx. Is that indeed 15 pi over 2? It is indeed 15 pi over 2. That's all there is to it. That's the disk method. And part B is just going to be the exact same thing, but what happens if we rotate about the y-axis? It's not going to be the same. So same region. We have the same picture, really. I'm going to copy it down here with a slight variation. And we're looking from 1 to 4. But now we're rotating it about the y-axis. So here, we have that. I did not give myself enough room. Can I fix this? Maybe. Hold on. Hey, how about that? Getting rotated about the y-axis. And now what we have, we're starting here, going up to here, and we're rotating it about the y-axis. So now it looks kind of like this. It's really squished. And again, now we still have circular cross sections. At any height, oh, what's C and D? What are our heights? Well, this is the square root of 1. And this is the square root of 4. Okay. So the disk method still says the volume is pi, but now it's the limits, everything's in terms of y. We're revolving it around the y-axis for the disk method. Y is going from 1 to 2 now. And now it's a function of y squared. Well, what is that? We know y is the square root of x. So x is y squared. Now this becomes y squared squared. Again, this is our g of y if you want. We're just using this formula over here. We need things as a function of y. So we get things as a function of y. And we say that for any y, the x coordinate is just y squared. And that's true if we look at this blue part of the curve. At any y value, the x coordinate is just y squared. Y of 2, x coordinate is 2 squared. And now we just simplify. This becomes the integral from 1 to 2 of y to the 4th dy. Power rule, 1/5 y to the 5th from 1 to 2. We can factor out a pi over 5 in front. And we'll get 2 to the 5th minus 1 to the 5th. And get 31 pi over 5. We should really be including units cubed on all of these. I haven't been doing it in these videos. But we are talking about volumes here. Now, these aren't the same answers for A and B. 15 pi over 2, 31 pi over 2. This is like double almost, or more than double. Oh, no, it's not. This is about 6 pi, and that's about 7.5 pi. The second volume is smaller, but that's fine that they're different because they're different solids, right? This blue solid is completely different from this blue solid. Even though it's the same function. Oh, no. This is the same. I used a different region. I wanted this region, but I do need to change the wording of the problem in order to give this. So there's no panicking, no panicking. Let me just say where R is a region bounded to the right by F, the left by the y-axis, below by y equals 1, and above by y equals 2. So it's actually a different region that we're revolving. Because if it was the same region, if it was this region, if it were this region we're revolving about the y-axis, we have to use actually the washer method, which is the next video. So I actually wanted, for the second part, for part B, I wanted this region rotated. All right. So it's fine. I just wasn't clear on what I wanted for the region, but the idea is the same. Let me know if you have any questions, and that's the end of the video. Bye-bye.